So we have a lot to cover today. We're going to be covering chapters 14, 15, 16, and 18. They're short chapters, but still it's quite a lot of concepts, so let's get down to it. All right, so we've been looking at these binary variables and regression models, and we've been looking at interactions and confounders. And sometimes people get confused, so I thought a visual display might help. So let's say we're trying to figure out if x, like if some x causes some y, all right? So each of these are displays of x, how x is correlated with y. And if we're trying to figure out a causal relation, and we have two prior groups that were formed before, like let's say A, see how you have two groups here, A and B. We can say A and B, A and B, and A and B. We have these two different groups that were formed first. Combining the two groups can give an overall regression effect that's very misleading. Okay? And an overall regression effect that's misleading. What do I mean by an overall regression effect? I mean, like when you combine these two, the overall, do you see what the overall would be? The overall regression would see this as almost like 1 point, and that is 1 point. And you would get this overall regression effect. I'll draw it in pink. This overall regression effect looking like that. And that can be misleading because within the two groups, there is not a positive correlation, right? Does that make sense? All right, so that's the overall regression effect. And then the interactions can, people say sometimes that can be confusing too. What is an interaction? That means when X has a different effect on Y for group A than it does for group B, illustrated by non-parallel within group slopes, non-parallel. So different slopes within the groups is an interaction. Different slopes within the groups, okay? That's how you think about an interaction. Non-parallel within group slopes. So for example, why don't we do an eye clicker and you see which one of these do you think in plot 1, 2, 3, and 4, which one do you think has an interaction effect? So I'm going to do an eye clicker on that, and let's look at it. So we can start it right now. So which of these plots, plot 1, plot 2, plot 3, and plot 4, have, which one do you think have interactions? So they're the same picture as what you have in your notebook. Okay, I'll just give you till 45 seconds on this. So everybody just pick one of them. I'll give you a few more. I see some of you are just coming in. I'll give you for 1 minute till 1 minute. There'll be plenty more eye clickers, so if you're just coming in, it's okay if you miss this. Okay, so let's stop it. And the answer is which one? Plots 3 and plots 4. So that should be D. Where did, shoot, I didn't see how many of you answered that. Darn, oh well. Okay, so plots 3, any questions on that? Oh, yeah, I can do it right here. Okay, thanks. Great. D. So the majority answered that. Thank you for seeing that. This thing moved around. Okay, any questions on that? All right, so those are the ones that have interactions. So let's go back to our document camera for just a minute, and let's look at that. Okay, so the do you see why there's no interaction here? Because they have the same parallel within group slopes. Here, they also have the same within group slopes. But here, plot A slope is down like this, and plot B is up. So that has an interaction, and this also has an interaction term, because these are non-parallel. They're not the same. All right? So this has an interaction, and this one has an interaction. Now, the next question is going to be confounding. So how are you going to think about confounding? Well, for confounding to happen, there have to be two conditions. Condition one, right here, is different x averages for the two groups. So for example, what do I mean by that? Do you see how these two groups, the average for A, the x average, is like right here, and the x average for B is right here. So they satisfy different x averages. And the other condition is 2 right here, that the overall slope is not equal to the weighted average of the two group slopes. All right? The overall slope that we're coloring this way is not equal to the weighted average of the two group slopes. The weighted average of the two group slopes. Let's look at that. So what would be the weighted average? We'll color that in orange. What would be the weighted average of these two group slopes? They're both slopes 0, so the weighted average would be 0. We could draw it in if you want, but it's both of these slopes are 0, so the average is going to be 0. So you can see those two are not equal. Basically, remember, for confounding to occur, the confounder is this group membership. It has to both be basically causing x and y, and that is these two conditions here. It's influencing both x and y. All right, so let's think about it. Why don't I do an iClicker, because I want you to think about it first before we fill it in here. So let's go to the back here, and all right, so question 2, I'll give you a few minutes to think about this. Which plot has confounders? Which plots have confounders? Remember, those two conditions have to be met. And right here, I'm just showing you the individual. This is the individual group slopes. So the two conditions, we did it with this plot already. We said, okay, different x averages is one condition, and the other one is what? That the weighted average is different than the overall average. Can you see what the overall average would be for this? It's pretty obvious what the overall average would be. For this one, what would the overall average be? Basically, it sees a group up here, the overall, you see a group up here and a group up here, and it's going to have some kind of overall average, so it's going to look like that. And the overall average here is going to be what? The overall. This looks just as negative as it is positive, so the overall would just be, it's as if it's just one symmetric blob, right? Isn't this going to cancel that out, and the overall average would just be what? As x gets bigger, your best average for y would be just like, I think it would just look like a flat line, right? So choose one of these, and let's see what you choose. Let's stop this. Okay, and the answer is going to be what? Which ones? 1 and 4, right? Let's see if you got that. That's C. Great, great, terrific. Most people got that. All right, so. And which plots have confounders? Only 1 and 4. Why? Just these two. Because they have to have different x averages. Does this have it? That eliminates plot 3. Group A, think about group A stretches in the x direction. It stretches across this way in the same. Do you see how they both have an x average of about here, the same x average? So that eliminates plot 3 right off the bat. Now let's look at the condition 2, that the overall slope, and I drew in these overall slopes here. Here's the overall slope, is not equal to the weighted average of the two. Do you see how the overall slope and the weighted average, the overall is going to be, these are all these points are on a line, basically. So the overall and the weighted average of the two are going to be exactly the same, even though they have different x-averages. What about this one? The overall, as we saw, is this pink one, and the weighted average, isn't that going to be exactly the same? So plot 3 is eliminated because of the both conditions. All right, so let's write that and think about it on our graph here. And let's go back to the document camera. Okay, so let's just draw that in. First, let's look at the overall. So these both have interactions. And this one has no interaction, but this has only confounding. How about this one? This one doesn't have either. This has neither. Right? It has no interaction. They have the same. And the overall is exactly the same as the weighted average because they both have the same, it's the same thing. All right? Maybe this is a little bit confusing. Let's just do a little key here. So that's the overall slope. Just the slope of x and y ignoring group membership. And then this is the weighted average of the two slopes. So this is the weighted average of the two group slopes. Okay? So how about here? So here, this one's pretty, the overall, this pink one, is just going to be, it sees, basically it's going to look something like that. It sees a positive slope. But the weighted average is just this, basically, I put the same number of points in each. If there weren't, that's what I mean by weighted average. If there are more points in one or the other, but I put the same so you don't really have to do the weighted average. You can just do this has 0 and this has very strongly negative, so it would be sort of a not as strong negative, but it would be something like still negative, but not as strong as that. Okay, and those clearly aren't the same. But here, this is the one that I think confuses people. This one has no confounding. It just has an interaction. So this has both an interaction and confounding. So this is interaction and confounding. This is both. And this is only interaction. Now, what do I mean by there's no confounding? You might think, well, this is confusing. But basically, when you look at this, you get an overall slope. The effect of x on y is pretty much 0, because this count, and that's also the same as the weighted average. So what I'm saying is, how can you think about this? It's telling something truthful here, right? It's saying that, you know, overall, there really is no effect, because the effect on x and y is just as much negative for group A as it is positive for group B. There is an interaction term. So this is this, for example, there's no confounding. That's truthful. That gives you information. Think about, you know what's a nice analogy that to help put this into perspective is when you have like a pre-election poll. You might see that overall, both candidates are pretty much neck and neck. But that doesn't mean within subgroups that they're neck and neck, right? You know, among Democrats, I'm sure the Democratic candidate is favored, and among Republicans, I'm sure the Republican candidate's favored. But overall, when you put them together, if it could be neck and neck, it could be just neither group is favored. But still, you want it. So the interaction term gives you some information, but it's not, as opposed to something like this, that would say, this is saying that x overall has a positive, there's a positive correlation between x and y. But it's bogus, because there isn't a positive correlation anywhere. If you just look at A alone, there's no positive. If you look at B alone, there's no positive. So it's really a bogus, you can't say that x has a positive correlation with Y anywhere. It's just due to confounding. So it's mixing it up. It's something, confounding is a false, basically a false correlation. It's giving you information that's just wrong. It's confounded, it's mixed up. Does that make sense? Whereas an interaction is giving you good information here. If there's no confounding, it's giving you good information. Think about, I mean, you're involved in an experiment where this is going on right now with the online versus the in-person classes. Overall, after I've removed confounders, it looks like, and at least in Stat 100, that the students, confounder being the people who sign up for the online, tend to have a higher math ACT score. But after we remove that confounding effect of, they're smart, they're better math students to begin with. It's not the effect of the online class, probably. This is what I think so far. I have to check it out further. But that doesn't mean that, so let's say there's no overall effect. There's no overall effect. But that doesn't mean that within certain subgroups, the in-person might be better for certain groups of people, and the online might be better for other groups of people. That would be interaction terms. And that's what we're trying to get at. Those aren't the same things at all. So it's possible that there's no effect overall, but that doesn't mean that I shouldn't advise certain students to take the in-person and certain other students to take the online. That's what we're trying to get at now. I mean, that was the purpose, mainly, to just help students make informed decisions based on the evidence. And I hope that will happen. But I think it just, so you can have overall no effect, but that doesn't mean that within particular subgroups you don't have strong effects that you want to get at. Whereas if there's confounding, like when we first looked at it, we said, oh, the online's so much better. And people, just because the students were outscoring it, people believed this. And said, no, it's not, because they weren't randomly selected. And if they're randomly selected, all those confounding, there was a self-selection bias. And I think that's what's going on. I think that both methods, overall, they're probably equal. It's just that certain groups might benefit from one or the other. Okay, so that's the idea. And so it's this type of thing helps people look at that and think about it. All right, so let's move on. Now let's look at chapter 15. So, chapter 15, this is interaction terms in their very simplest setting. It's two binary X predictor variables, explanatory variables, and a quantitative response variable. This is also known, if you're taking other courses, this is known as a two-way ANOVA. We haven't even started ANOVA yet, but what's typically called ANOVA. But this is, you're jumping right into a two-way. You've already seen a one-way. We'll look at that later, but that's basically we have two categorical variables predicting a quantitative variable, all right? So, and it's a very nice way to help you understand interaction terms. All right, suppose subjects were randomly divided into 4 groups. Drug A only, just getting drug A only, drug B only, both drugs, and neither. And the duration of some disease was recorded. So the longer, how many days people had the disease for. Okay, so the table below gives the mean responses for 3 types of models. All right, the 3 types of models are like no drugs are given, just drug A, just drug B, and both. All right. And here, excuse me, this is the model right here, and this is how it came out from this data. So we wanted this regression equation fits this data. Okay? So the effect of the 2 drugs equals the sum of their parts, and there's no interaction effect. That's what this is showing. Why? Okay. What it's saying is that, first of all, I'm sure you've already heard of 2 drugs having an interaction on each other. Like, the doctors tell you, oh, don't mix 2 drugs together because there could be a bad effect when you do, because it's worse than the sum of their parts. They might work okay, they'll warn against mixing 2 drugs together because they have this interactive effect. Or sometimes 2 drugs they want you to take two drugs together because they enhance each other, and it's more than their sum of the parts. Okay? So this is just when there's no interaction effect, and it's saying what? That when you have neither drug, it lasts 10 days, okay? If you just administer drug A, then what happens? You cut off 4 days of your illness. So that's like -4. And if you just administer, so that's like this one right here, right? -4 equals 6. And if you had 8 minus 4, that's equal to 4. So that's that one. And the effect of B is 2. And you can see as you go from not having B, having neither, and then you just add B, B is 1. B is going from 0 B to, just means that the drug is present. Now it goes down by 2. And same, 2. And even when you put both of them together, it has the same effect, right? It just goes down still by 2 or by 4. There's no enhanced effect, or there's no interaction effect. And you can see the parallel slopes. We can draw this here, I'll show you how to draw this. So let's say we have, on this axis, we have A, and A goes from either being absent or present. And on here we'll have Y, the number of days, okay? This is our Y variable, so this is what we're measuring. This is the number of days. Okay? And when you have, when A is 0, and we'll draw 2 lines. So when B is 0, you get, let's say you have 10. The duration when A is 0, it goes from what, 0 to 10? So we'll go 0, 1, 2, 3, 4, 5. 6, 7, 8, 9, up to 10. All right? And so let's just look at when B is 0, right? B is 0 along here. So when A is also 0, you have 10. But then when A is 1, it goes down all the way to 6. 6 days. So it reduces it by 4. The effect of A, this is when B is equal to 0. The effect of A, when B is equal to 0, B 0, A adding A just makes you go down to 6. Okay? And how about when B is 1? When B is 1, you start off at 8 right here, at 8 days, and it's the same exact effect. It will go down by 4 all the way down to, it's totally parallel. And it goes down to 4. Okay? So those are parallel slopes because there's no interaction term. All right, now let's look at these two. And these are called non-additive models because they include a multiplicative interaction term. There's your it's A times B. All right? And you can see, like, now what happens? Now we have the same thing. 10 minus 4 equals 6, right? That's the effect of drug A. That's still that. And 10 minus 2, that's this drug. Still 8, right? But now, what should I put in here? Well, it doesn't look like this is when A and B are both 1. So put in a 1 for drug A and for B, and 1, and you'll get what? 10 minus 4 times 1 minus 2 times 1. Right here, that would have given us what we had right here. But now, what do you think? We're going to also bring it down 3 more. Minus 3 times 1 times 1. And that is equal to what? 1. That's the interaction effect. Okay? So now if we graph it, we can graph it here. So let's graph it here. Do the same thing that we did here. And you can see they're not parallel slopes. So this is A, and it goes from 0 to 1. And we're going all the way up here to 10. Here's 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. And so now we have 10 goes to 6 still. 10 when b equals 0. We still have that line here. But now what happens when b equals 1? We start off at 8, but we don't go down to, it's not parallel. We get all the way down to 1. So it's not at all parallel. So this is 6. This is 1, sorry. 6 and 1. That goes all the way down to 1, from 8 to 1. And this is when b equals 1. So they're not parallel slopes, because we have an interaction term. And this, in this case, the y variable is a bad measure of how long your disease lasts. So this, the doctors would say, take the two drugs together. Okay, this looks like, this is number 1. This goes all the way down to 1 there. That's what that says. All right, any questions on that? And we could have here, you could have the effect of the two drugs is worse than the sum of their individual parts. Worse, because look, we have the same thing here, but now this is going to, you have 10 minus 2 is 8, and 10 minus 4 is 6. But when you take both of them together, it's not just 10 minus 4 minus 2. That's an additive effect, right? Adding 4 and 2 together, and then you would get the 4. No. Now it says plus 7. And that brings you all the way up to what? 11. So that's worse than taking nothing. And that's a bad interaction effect. And so the picture would look like non-parallel slopes again. You just do the same thing again. So you go from 0 to 1 on A, and you go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's your 10, there's your 8. And so you'll still go from 10 to 6 when b is equal to 0. Start at 10 and you go to 6. But now you start at 8 and you go up to 11. That's 11. And that's when b equals 1, and this is when b equals 0, this line. Does that make sense to everybody? This is a line. And this is your line would be. You see, the interaction effect only kicks in when both A and B are 1. All right, any questions on that? Does that make sense? Sorry this graph is messy, but you can see that there's not parallel slopes. 10 minus 4 and 8, as you go over 1 in A, you don't go down 4 in Y. In fact, you end up going up 3. Okay. So now let's do the next page as iClickers. All right, let's do this one together. First, we'll do this one as an iClicker. So suppose A and B are two treatments designed to boost scores on some exam, coded 1 if given, 0 if not, okay? The numbers in the table indicate the average boost from each treatment by itself, from both together, and from neither on your exam scores. So now a higher number is good. It's a positive effect. Fill in the blanks so the model and the data match. So this is, what would you put in here? In this square, it's what? When A and B are both 1, and there's no interaction, so it's pretty easy. Just put a 1 in and a 1 in for both, and what do you get? 50, right? +20, right? Does that make sense? All right. How about let's do this one as an iClicker. What would that have to be to match that? So we'll go over to the PC and get rid of this and put this one up. Okay, just I'll give it just a few more seconds. Okay, we'll stop it. And what's the answer here? The answer is 10, part C, right? Great. Terrific. You got that down. All right. So now, let's see, is there any more here? No. We're on to chapter 18. Okay, so let's go over to the next one. And let's go over to the document camera and fill that in. All right, so you all got that one, or most people got that one. If you just put, the easiest way to do it is just put a 1 in for A and B and 1 in for A and B there, and you say 20 plus 30 is 50, plus 10 makes 60. All right, so now, and that's your interaction term, no interaction term. It's more than the sum of the parts. It's not just 20 and 30, it's more than that. Okay, so let's look at this. So how would you do this one? This one has a blank here and a blank up here. The easiest way to do it is just to start with when A and B are both 0. So when A and B are both 0, what does the intercept have to be there? Has to be 2, correct? So just put a 2 in there. Then, as you go from 0 to 1 in A, you're going to be adding, what, 6. You could look at this spot and say this spot has A equal to 1, B equal to 0. So 2 plus 6 equals 8. Same here. What do you think 2 plus 8 equals 10? So it has to be 8. Right here has B equal to 1 and A equal to 0. So 8 plus 2 is 10. And there's no interaction term here. So you can just add it. 2, it's just an add, plus 6 plus 8. So that's 16. Parallel slopes, you can see it. 2 plus 6 equals 8. 10 plus 6 equals 16. Or 2 plus 8 equals 10. 8 plus 8 equals 16. Parallel slopes. All right, let's look at this one. There's no interaction. It's very easy. And there's no interaction here. Very easy. So what's this one going to be? Just put in 1 for both of those, and you start off 5 plus 30 equals 35, plus 30 equals 55. You can just put a 1 in for both of those, and you get 55. All right. So here, I'll just give you a few minutes so you can do this on your own, and just help each other if you want. Fill this in, and raise your hand if you have a question. I'll just walk around. I just did. So we're starting in right now at chapter 16, and we're going to do chapter 16 and 18, and then I'll refilm for you chapters 14 and 15. All right, so we're talking about multiple regression, and we're modeling. Right now we're taking a single y variable, a quantitative y, just like we've been doing before, but now we're going to have two or more x variables that are quantitative too, not just zero. Before we added a 0, 1 binary variable. Now we're going to look at two or more quantitative predictor variables. All right? So let's just remember, when we just have simple regression, we have if we have a quantitative x predicting a quantitative y, we have a scatter plot. And if it shows a roughly linear trend, we can write this regression equation, right? But now suppose we want to estimate y using two quantitative variables. And the example we're going to be doing is, let's say we want to estimate your final exam scores, but we want to make a prediction using both homework and exams to predict final. Okay? So let's say I wanted to predict your final exam score from both your homework average and your exam average. That would look like this. And before we even do this, I want to show you what the picture would look like. So we're going to go to chapter 18, skip ahead, because I think it will be helpful to just think about it. So this is a data set. This is a multiple regression scatter plot where we're predicting final exam scores from 107 students from their homework and their exam scores. So now look, we're in 3D space because we have a final, homework, and exams. We have three variables. So basically, given their homework and exams, we're estimating their final scores. And the scatter plot shows their final exam scores as vertical distances from their point in the homework and exam plane. So for example, you can see this person right here on his homework. Oh boy, this person did not do very good. Let's look at this person right here. On their homework, they got below with like, oh, I don't know, 38 it looks like. And on their exams, they did better. They got a 70. And it looks like they got about a 70 on their final. Okay? And so now if you look at this, what are we trying to do here? When we're not trying to fit, what do you think we're trying to fit here? So this multiple regression equation, we got this equation that says their predicted final is equal to some intercept plus 0.1641 times homework scores plus 0.5824 times exam scores. And what do you think it is? It's the best fitting what? Through all the y's so as to minimize what? Let's do this as an eye clicker. See if you can visualize what we're trying to fit across here. Okay? Remember, with 2D we fit a line. Now we're in 3D. So let's see. Let's just do an eye clicker and see if you can think about that. And so, all right. So with this one, I say your final is equal to, this is the same equation, plus some error, right? And the above equation describes the best fitting what? Through all the points so as to minimize the squared errors in what? So just select one of these for the first blank. What do you think we're trying to fit? What do you think this is the equation of? It's in a cube, but what do you think we're trying to fit within the cube? Okay, so now let's see, let's stop it. Everybody had a chance to vote, stop. All right, and it's a plane. Okay, well, most people got that. Now let's look at the next one. It's a plane. And the next one says, all right, now, so it's the above equation describes the best fitting plane through all the points so as to minimize the sum of the squared errors in what? In the exam scores, the homework scores, the final scores, all of the above or none of the above. We want this second blank. What are we trying to minimize when we're doing this? Okay, so whoops, go ahead and we'll stop it. And look what I just did. It's right here. So which one of these? What are we trying to minimize? Errors in what? What are we trying to minimize the errors in? Okay, so we're going to stop it. And it's in what we're trying to predict, which is the final score. So it's C. Excellent. All right, so now let's just go back to our document camera here and write that in. So it's the best fitting plane so as to minimize the squared errors in Y in our final scores, which are Y in finals. And you can see that when we turn the page. So let's turn the page and you can see the plane. So here's the picture of the regression plane. You can see this regression plane here. You probably can see it better in your books than on the screen here, but you can see a plane in there. We're trying to minimize our prediction. You see these little points, these vertical distances above and below the plane. Like, look at this person. Wow, this person soared up and got a really high final. That's a very big error. What? We predicted very low because the person only got what, 45 on their homework, and what, about an 80 on the exams, but he got a huge, almost 100 on the final, so he really came through. That's a big positive error. Here's a big negative error. This person was predicted to do much better. Okay, so now let's look at this for a minute. And do you see notice how the slope of the homework, which is a very mild slope right here of 0.1648, that's the tilt in the plane as you go from 30, that was the lowest homework, to 100 on the homework axis. See this, like right there, that has this tilt. That slope is right given by that. Okay? Whereas you go from, on the exams, this slope right here, see how much steeper it is? There, that one. And that's the tilt of the plane as you go from 50 was the lowest to 100 on the exam axis. Notice how the exam tilt is bigger. That's because the exams are a better predictor, stronger predictor of the final than the homework. Okay? We can compare the tilts because all the variables are expressed in the same units. So that's the visual. And now let's look at these coefficients and see how they compare to in the simple regression, because this is the same example we've been working with from called the grades. That's a data set we've been working with before. So let's go back to page 81 and understand those slopes in the multiple regression equation. All right. So now the first thing that I want you to notice is that the slopes in the multiple regression equation are not the same as the slopes in the simple regression. We've already seen this on page, as we've seen on page 71. So we've already seen that. Just to refresh your memory, on page 71, we did this, we looked at we saw the slopes weren't the same. We were looking here. We had these two simple regressions. One was predicting y, the number of pairs of shoes people have from whether they're that binary variable, gender, and one was predicting it from shoe size. And we saw that this slope, this had a very strong negative correlation and a big negative slope. When we put it into the multiple regression, down here, it almost went away. And it was no longer significant. Okay, so it changed. All right, so now we're going to look at this again. We're going to look at how they change in more detail. Okay, so we're going to expand on this simple regression example where we used exam averages to predict final exams. We've done this exact example before, but using a slightly different, it's a slightly different data set. It's basically unrounded numbers. So we already did this, if you want to look back on page 33, but with rounded numbers, just as a simple regression inference problem on page 33. So it's this problem, but I rounded the numbers. Okay? And I said 100 students. There really were 107. So this is the actual unrounded actual data set and the unrounded numbers. Okay. So here it shows the average and the standard deviations of homeworks, exams, and finals. And we're going to use two variables now to predict finals, both homework and exams. So, all right. Now, for simple regression, do you remember how we defined the correlation coefficient R? Do you remember like how you calculate that? It's the correlation between two variables, x and y. If you just have simple regression, and what you do is you change x and y to z-scores, to that standard measuring stick, right? You change it to it. So you want to look at the correlation between the two. You have to have the same measuring stick, so you change them to z-scores. And then the correlation is the average of their products. Zx times zy, the average of all their zx's times zy's. And it can either be negative or positive. It ranges between -1 to +1. Now for multiple regression, we have 3 variables now, right? We have an x1, an x2, and a y. So correlation is only defined on 2 variables. We have 3, so what can we do? What can we do? Well, for multiple regression, you have this big R. It's the same big R we've been talking about, this correlation coefficient. And what it is the correlation between your actual y's and your predicted y's from the regression equation. This is the only type of correlation that makes sense when we have more than one x variable, since correlation is only defined between 2 sets of numbers, not 3 or more. So now we have 2 sets of numbers here. We have look at down here, it says this is a little y and this is a little y with a hat on it. So you have 2 sets of numbers that you change to z-scores. You change them both to z-scores the usual way. And now you can compute the correlation coefficient, but it's only positive. And for simple regression, it's exactly, for simple regression, capital R, we've been using it, it's always positive and it's the absolute value of little r. And capital R can only be positive since our predicted y's are always positively correlated with our actual y's. Why? Well, because we're trying to make a prediction. They're going to be positively correlated. Even if there's a negative correlation, like there's a negative correlation between your, how many you get right on an exam and how many you get wrong. So let's say I wanted to predict how many you got right on the exam from how many you got wrong. Well, there's a negative correlation there, but I'm going to be predicting, my predictions are going to be positively correlated, in fact, perfectly positively correlated with your score, with how many you got right, knowing how many you got wrong. So they'll always be, because you're trying to make a prediction that's close to the actual value. It's positively correlated. Suppose we wanted to predict final scores from homework and exams using a multiple regression equation of this form. What will R be? Well, then R is going to be the correlation between your final scores predicted by that equation we get and your actual final scores. And of course, the stronger R is, the better it's a measure of how good our predictions are. Does that make sense to everyone? All right, so now when you have two predictors, x1 and x2, and a y, you're going to have three simple R's, three simple correlations that are not the same as this capital one, right? You'll have the correlation R between y and x1. You'll have the correlation between y and x2, and you'll have the correlation between what? x1 and x2. How they're correlated together. Okay? So let's highlight that. This is the main idea there. And so before we begin, what we're going to be doing is we're going to be comparing these two simple regressions. These are both predicting y from x1 predicting y, and this is x2 predicting y. So here you have x1 predicting y, and here we'll have x2 predicting y. Okay? So first let's look at the two predictor variables separately, like we did for simple regression. And like we did on page 71, we looked at them separately there, too. We did it before with the binary. We see that both, I'll write that, and in chapter 12. We've already done that, okay? Now, why does that look so? Okay, so we see that both scatter plots show a positive trend, right? A positive trend. They have a pretty strong correlation. This is even stronger, right? What do we gain by combining the two separate equations into one? Well, we get a better prediction because we're combining information from two predictors, right? We get more information when we combine them. And we also can look at the effect of each predictor while controlling for the other one, keeping the other predictor constant. So we did this before, so you get more information when you combine them, because you can see the effect, you can separate out the effects of each. And we get a different coefficient when we control for the other predictor. In some cases, as we'll look at later, multiple regression coefficient will give a better estimate of the causal effects than do simple regression coefficients like we did. That's what we did. We already did that, like in the shoe example, where the slope for shoe size pretty much disappeared. Was no longer significant in the multiple equation. So we did that. Now we're just doing the same thing for quantitative variables. All right. So this is the equation we just got, and look what you see. You see that this right here, it went down, right? It's not the same as it was in the simple. And this also went down. It's not the same. Okay? In multiple regression, we're going to let the computer software calculate these slopes for us, since we'd have to adjust for the R and the SDs we used before to account for the additional variable. And the calculations are really tedious. I'll explain the idea below so you'll see why, but they're really tedious, so we're not going to do them. We're going to let software, but you'll see how it works, and I'll explain it, the idea, okay? But we're going to let the software work it out for us. But do we have the same slopes as we did in the separate equation? Do we? No. We don't. They dropped. See? See, what we're looking at is these right here. They dropped from what they were in the simple. They both got smaller. Why did the slopes change? Why did the slopes change? Oh, that's a little bit difficult to explain, but we're going to explain it. They change because they're correlated with each other. And remember what we're doing here. What we're doing is we're looking at we're separating out the effects. When we look here, this slope says that homework has pretty strong effect, but that's because people who do well in the homework also will do well in the exams, and it's not separating out those two effects. Same with this, people who do, so it's combining. Some of the effect here is due to the exams, and some is due to the homework. And when we separate them out, we get this slope. They're called partial slopes. This is the effect of the homework after the effect of exams has been partialed out or controlled for. And this is the effect that's left. So they change. Why do they change? Because they change because they take into account how the homework and exam averages are correlated. So they change when they're correlated because R for the x1 and 2 is not equal to 0. So let's look at this what's called a correlation matrix here. And it shows how all three of them are correlated. Okay, we've had those three correlations. Now when you look at this, why is that diagonal all 1? Notice this diagonal is 1, why? Anybody know? Yes? Exactly. So the way you read this is you say, homework is correlated with homework. You can perfectly predict homework from homework. So why? Because the correlation between x and x is equal to 1. Do you notice also that there's symmetry here? See, okay, so all these are 1, but you see how, like, for example, this is the same as that, and that's the same as that. So the off diagonals are the same. Why? So the off diagonals are symmetrical. Do you know why that would be? Can anybody figure out why those off diagonals are symmetrical? That says off diagonals are symmetrical. And I want to know why. So like this is, what is this saying? Homework predicts exams. And what's this one saying? Exams predicts homework. Right? And see how these two are the same? That and that one. And that one. These off diagonals are, if you know these, you know those. Why is that, do you think? Because predicting the correlation between x and y is the same as between y and x, right? And that's because the correlation between x predicting y is the same as between y predicting x. All right, so we have three correlations we have to take into account. Homework and exams have a correlation of that. Okay, so that's this one. Where is that on here? It's right here. Whoops! Look what I just did. Darn. Unpink it. All right, it's these two. Uh-oh. Anyways, all right, so now here's this scatter plot relating homework and exams. So this is relating homework, which is x1, and exams, which is x2. And it has this correlation that I just showed you, right? And here is the equation, all right? Now I'm going to show you, let's focus on, even though we're not going to be actually computing these slopes here, I want to show you how you can get from here back to there, how they're related, okay? So, and what it means. So the homework slope in this multiple, what this is doing, it's controlling for exams. So that means for people who have the same exam, let's say have 80 on the exams, this is how much homework affects them. So for each extra point of homework, their finals on the average go up by 0.1641 points for those who have the same homework scores. Similarly, this slope right here says that for people who both have the same exact homework scores, the exams, 1 point more in your exams will affect your final more. Predicts 1 point, if two people have the same exact homework scores and one of them has 1 point higher on the exam average, then you can predict on the average that their finals will be more by 0.5824 points. Does that make sense? Okay, so that's what that means. Whereas in the simple regression, it ignores, this slope here ignores their exams. Okay, so another way to think about this is after we predict the finals from the exam averages, like here, this is ignoring exams. When you go over here, it says, okay, after we're done, after we've already predicted the finals from the exam average, how much more does homework help us make that prediction? And that's why that's going down. Okay? So the question is, I want you to think about is, when would the coefficients in the two separate single regressions be the same as the ones in the multiple regression? When would they be the same? Like, when would this not change? Can anybody figure that out? It's kind of a hard question. Go ahead. Yes, exactly. If they're not correlated, they're not going to change. I think that really good answer. That's so when would they not change when they're not correlated? So here's how can we think about this? Okay, so you have these two separate single regression equations. Let's think about them this way. So you have homework predicting the final, and you have exams predicting the final. So, so when would they be the same as, so think about it, when you combine them into the multiple regression equation. So when you're in the multiple regression, if they're not correlated, so if the correlation between homework and exams between x1 and x2 is equal to 0, you would have a picture, you could have a picture that would look like, I'll just make it like this, like homework would be predicting finals, and it's knowing something about the homework tells you nothing about the exams, so they're completely separated. And you have exams predicting finals, and they'd be separate. Do you see how it wouldn't change? Whatever effect they have would be the same in the multiple because they're separate. So when that's equal to that, the slopes in the multiple regression would equal the slopes in the simple. Does that make sense? But like if, let's say they're correlated like they are, but if the correlation between x1 and x2 is not equal to 0, well then you're going to have a situation where knowing, okay, let's say homework, part of the homework is mixed in, I could draw it this way, that might be the best visual, with the exams. And they're both predicting the final, so there's this overlap here. So if they're all positively correlated, like in this case, when you combine them, you'd be like double counting if you just use the same slopes again. So basically, the slopes are not equal. So the slopes in the multiple would not be equal to the slopes in the simple. Because otherwise, because part of that homework slope in the simple is it's correlated with the exams being higher. So after you, these are actually called partial slopes in the multiple regression. They're called partial slopes because they quantify the effect that each x has on the y after the effects of all the other x's have been controlled for or partialed out. So they're only partial slopes. That's what they call them. I say that right on page 85. Maybe we should highlight that because we're just thinking about that now. All right. So that's the idea. So is when they're correlated with each other, they could either get bigger or smaller. If they're all positively correlated the way I just showed you, then they'll get smaller in the multiple. So let's do this. Let's see how that happens. I think that would be helpful. So why don't we do this? So on the next page, we're just going to calculate that. All right? So what you would do, let's see how it works exactly. All right? Let's see how we get these numbers. So by working, dropping one of the predictors. Okay, so let's say we want to drop exams. We want to drop exams here. So if we want to drop exams, let's express right here exams in terms of homework. All right? This was the we got on the previous page. So we could put this in right here for for exams, and then we get an expression in terms of homework. We get 0.5824 times 0.3083 right here times the homework. And then if you add these two together, you'll get that number. Okay, that's what we did here. You can forget about, the intercept will change too, but we don't have to worry about that. So let's do, we could do another example down here. Okay, because we don't have much time left here. We can do this one down here, the same thing. All right, so now what do we want to drop out? Now we want homework to drop out. So instead of homework, we want to express something in terms of exams here, right? So we need to eliminate homework. We want to eliminate homework. So we'll have homework equals something in terms of exams. Something times exams plus the intercept. So how are we going to get that something? And that's what we'll put in there. Well, so we got to get the slope. This is like a homework problem, so I want to work it through for you. So you want to get the slope for that. which is r times the standard deviation of y over the standard deviation of x. So we have to look right here at the correlation between homework r, between homework and exams. We know that's this, 0.3933, and then we want the ratio of their standard deviations of y over x. So the standard deviation of the homework over the standard deviation of the exams. So that was given here. So it's 11.73 over 9.197. Let's put that in. So we can do that. $9.197. And I got 0.5016. So that's what we put in here. We want to eliminate homework, so this is what we're going to do. We're going to express, instead of homework, we're going to express that. And I wrote it wrong, sorry. It's 0.5016. So 0.5016. All right, so that's what we want to put right this. We want to put right in for homework in there. So now our second step will be what? We'll just rewrite this equation as final equals 0.1641. Instead of that homework, I'll put this in, times 0.5016 times exams, plus 0.5824 times exams, plus some intercept, right? So now we'll just add all this together. I multiplied these two together, those two together, and I got 0.0823 times the exams. And then I have plus 0.5824 times the exams, plus some intercept we're not worried about. And when I add these two together, I should get that. And I do. I get 0.6647, which is the same. This is the same as that. So that's the idea, is that I think you understand the idea. I just said it out in words, what we just did. And now let's just make sure you, besides this, let's see if there's anything else we need to really keep in mind here. And that's, yeah, this for sure. And here's what we said. If the different x's are correlated, yeah, this is all super important. We're going to have to beware. We'll talk about this next time, multicollinearity. When they're too highly correlated, you can run into real problems. So I'll highlight it to remember to talk about it next time. All right, so that's it. And sorry we went so long.